We're going to calculate the non-standard cell voltage using the Nernst equation. In this example, we are asked to calculate the cell voltage of a voltaic cell at a temperature of 25 degrees Celsius when it is prepared with 4.38 molar chromium 3 plus and 4.3 molar of calcium 2 plus. The cell is represented by the following redox reaction. They've given us a balanced chemical equation, but we have to determine which element is undergoing the reduction process and which element is undergoing the oxidation process. To do this, we have to assign oxidation states. So in this reaction, chromium 3 plus has an oxidation state of +3, calcium 0, chromium 0, and calcium 2 plus +2. Now we want to compare element to element. Chromium starts off at a +3 oxidation state and ends up with a 0 oxidation state. So there's been a decrease in oxidation state, and that would mean reduction. Calcium starts off at a 0 oxidation state and ends up with a +2 oxidation state. So an increase in oxidation state means oxidation. I also want to start off with a list of my given information. We are asked to calculate the cell voltage. We have temperature, but my temperature is in Celsius, and my initial temperature is in 1 decimal place, so we have to convert to Kelvin, and our converted temperature should also have 1 decimal place. We have the concentration of chromium 3 plus. We have the concentration of calcium 2 plus, and we have our constant R, and our constant F. We need a little bit more information. We need to calculate the standard cell potential, and we need to use a table that has the half reactions and the potentials. The tables list only reduction half reactions with their standard reduction potentials. So we're going to use the table, and we don't need to memorize this, we just need to use the table. And chromium is listed this way on the table. And its reduction potential is negative 0.74 volts, and calcium is listed as a reduction half reaction, and its reduction potential is negative 2.87. Now we're going to look at our balanced equation, and we see that chromium underwent the reduction process. So we're going to label the chromium half reaction as the cathode, and calcium that went through the oxidation process as the anode. We can go ahead and calculate the standard cell potential, and that's going to equal to the cathode minus the anode. I'm going to go ahead and plug in my numbers. And my standard cell potential is 2.13 volts. I also need the reaction quotient. Remember that the reaction quotient is the concentration of the products over the concentration of the reactants raised to the power of their coefficients. We do not include solids and liquids. So Q equals the concentration of calcium raised to the power of 3 over the concentration of chromium raised to the power of 2. I'm going to go ahead and plug in my numbers. And I get Q equals 4.144. Okay, I've gathered all of the given information that I need. Now it's time to use the Nernst equation, which is the cell potential equals the standard cell potential minus RT over NF times the natural log of Q. R and F are constants, but I need to figure out what that N is. N is the number of moles of electrons that get transferred to make that overall equation. So take a look at my two half reactions. In order for the electrons to cancel out, the electrons have to be 6. So there's a total of 6 electrons that are going to be transferred in this reaction. So that means N equals 6. So I'm going to go ahead and plug in all of the numbers I have now. I'm going to plug all of that into the calculator. My final answer should have 2 decimal places. 2.12 volts. Now what this means is the cell potential is positive, so that means under these specific conditions, this reaction, the way it's written, is considered a spontaneous reaction. Let's take a look at another example. In this example, we are asked to calculate the cell voltage of a voltaic cell at a temperature of 25 degrees Celsius when it is prepared with 0.1 molar of zinc 2 plus and 0.01 molar of copper 2 plus. The cell is represented by the following redox reaction. We need to decide which element is going the reduction reaction and which element is going to be assigned the oxidation reaction. So let's go ahead and assign our oxidation states. Zinc 2 plus is plus 2, copper is 0, zinc is 0, and copper 2 plus is plus 2. Zinc starts off with an oxidation state of a plus 2, and it decreases to 0. This is called reduction. Copper starts off at a 0 oxidation state and increases to plus 2. This is called oxidation. The next thing I want to do is list my given table. We're asked to calculate the cell voltage. We have temperature, but temperature is in Celsius. I'm going to have to convert this to Kelvin. We also have the concentration of zinc 2 plus, and we have the concentration of copper 2 plus. We also have our constant R. And our constant F. Okay, I also need some half reactions, so I'm going to have to take a look at a table for that. And remember that the table only lists reduction half reactions with their reduction potentials. So that means I'm going to use the table and get those numbers. And copper is listed as a reduction. And this is 0.34 volts. I need to know which part is the cathode and which part is the anode. So I need to take a look at my balanced chemical equation. We said that zinc underwent the reduction process, so we have to label the zinc half reaction as the cathode. And copper underwent the oxidation process, so that half reaction is labeled as the anode. Typically, we would say that the standard potential that is larger is the cathode, but we have the balanced chemical equation that we have to go by. So the next thing we want to do is calculate the standard cell potential, which is cathode minus anode. I'm going to go ahead and plug in my numbers. And this is going to give me negative 1.10 volts. Okay, I also need the reaction quotient. Remember, reaction quotient is the concentration of the products over the concentration of the reactants. So Q equals the concentration of copper 2 plus over the concentration of zinc 2 plus. I'm going to go ahead and plug in my numbers. And this is going to give me 0.1. All right, I have all that I need. Now it's time to use the Nernst equation. E equals standard E minus RT over NF times the natural log of Q. R and F are constants. N is the number of moles of electrons that got transferred. So we take a look at our half reactions. The electrons cancel out when they are 2 electrons, so N equals 2. I'm going to go ahead and plug in all of the numbers. I'm going to plug this into my calculator, and I'm going to get E equals negative 1.07 volts. So what this tells me is this reaction at these specific conditions is considered non-spontaneous, and I know that because my cell voltage was a negative number. So the way this reaction is written at these conditions, this reaction is non-spontaneous. Good luck and keep practicing.